Hello and welcome. This is Cambridge O-Level Physics Paper 2. Subject code is 5054. This is May-June 2022 exam, and this is version 1 of the exam. So let's start. Section A, it says answer all the questions in this section. The answer in the space is provided. Question number 1. Figure 1.1 shows a model of a human arm. The rubber band represents the muscle that moves the part of the arm XY up. The mass suspended from XY as shown in figure 1.2. The weight of the section XY is negligible and the model is at rest. So here what we see, what exactly figure 1.1, it is the model of a human arm. This is the rubber, this is the pivot point, and this is the section XY. Then we have suspended a mass M from the section XY, and it has moved a little down, and then so this is something like this. So this is 2 centimeters and this is 16 centimeters, and there is some weight or mass that W equals to mg that is acting on in this direction. It says state 2 ways in which the dimensions of the rubber band change as mass is added to the section. So two ways. So we have to find out 2 ways in the dimensions of the rubber band. So dimensions of the rubber band, it will increase, say for example, this is our rubber band. So the dimensions will increase in this direction, and it will also decrease in this direction. It will thin down and it will elongate. Okay, so let's write it. So how to write it? The rubber band will be stretched, will be stretched in the vertical direction. It will also get thinner, or you can say cross-sectional area will decrease. Okay, so 2 ways in which the dimensions. So for example, this is your rubber band. Okay, so this is your rubber band, and if the force is acting, it is stretching it in this direction, and it is also thinning it in this direction. So these are the 2 forces, F1 and F2, that are acting on the rubber band, and that is actually changing the dimensions. Then part 2, it says state the form of energy stored in the rubber band. So it is elastic potential energy or strain energy. So this is elastic potential energy or strain energy. Okay. Then moving ahead, part B, it says state the principle of moments. So the principle of moment, moments states that the sum of clockwise moments is equal to the sum of clockwise moments under equilibrium. Okay, so this is how you write principle of moments. Then moving ahead, part 2, it says explain why the force that the rubber band exerts on the XY, on the section XY is larger than the weight of the mass. Okay, so remember, this is how, this is the force or because of mass. This is the force because of rubber band. This is 2 centimeters. This is 16 centimeters. Okay, so the force, we have to explain it in terms of moments. So remember, say point P is our point, or point X is taking moments across point X. If we see this diagram, yes, it's point X. So if this whole system is in equilibrium, then the total clockwise moment, that is force because of mass multiplied by the distance from the pivot, is equal to force on rubber band multiplied by the distance from the pivot. Okay, so this distance is much smaller than this, then it means that the product in which the force will be much greater than. So we have to explain this in terms of words. So the distance between the pivot and point where rubber band, or in the better way is to write the distance from pivot or the moment on the rubber band is much smaller than the distance of moment for the mass. So to establish equilibrium, the force on rubber band should be much larger than the weight attached. Okay, so moving ahead, part 3, it says mass suspended from section XY in figure 1.2 has a weight of 4 Newton. So calculate the force that the rubber band exerts on the XY section. So what we have here, so we have a system like this. So this is our pivot point X. This is the mass, and this is 4 newtons. that is acting in this direction. Then we have the rubber band F, I call it F band. So this distance is 2 centimeters. This is 16 centimeters. Okay. So this is the system we have. We have to find out the force that is acting or that is acting on the rubber band. So how we're going to solve? We are really going to solve it. So taking moments across X. Okay. So taking moment across X, we have anti-clockwise moment is equal to clockwise moment. So anti-clockwise moment, we have 2 centimeter multiplied by force on the rubber band. And this is equal to clockwise moment. We have 2 plus 16 centimeter plus, oh sorry, multiply by 4 newtons of force. Multiply by 4 newtons of force. So the force comes out to be F on rubber band 18 centimeter multiplied by 4 Newton divided by 2 centimeter. So the answer will be 36 newtons. So the force answer comes out to be 56 newtons. Okay. Again, do not forget to write the units. Moving ahead, part 4, explain how your answer in B3 is different when weight of the section XY is not negligible. So remember what we are now, what if weight, so in this, what we have assumed, we have 4 Newton here and we have F force acting on the rubber band, that is 36 Newton in this case. And this was 2 centimeters. This was 16 centimeters. Okay. And this one was our XY. So if we include the weight, because we have what we have done, we have made this XY bar as of negligible weight. So if we include the weight will be acting downwards. So this will be the weight of the bar. So this will be doing what? So this is, for example, 9 centimeters. So this will be increasing the clockwise moment. So this will increase. So to compensate it, the force on the rubber band will be actually more. The force on the rubber band will be much more than what we have calculated. So using this, now let's try to write in words. Explain how the answer will be different. So the force on the rubber band will be greater the clockwise moment will increase, or even the sum of clockwise moment will increase. This increase will be compensated by extra or by increase in force on the rubber band to ensure equilibrium. To ensure equilibrium. Okay, so this is how you answer this question. So moving ahead, question number 2. It says figure 2.1 shows a wind turbine. The turbine blows directly towards the wind speed with a speed of 12 meters per second. In 1 second, 6,000 kg of air passes through the circular area swept by the blades. Calculate the kinetic energy of the air. So remember, kinetic energy is given by half mv square. So we have been given by the velocity. So here the velocity is 12 meters per second and mass is 60,000 kilograms. So the value will be half into 60,000 multiplied by 12 square. So the value comes out to be 4.32 into 10 to power 6 joules. We can also write it as 4.32 megajoules of energy. So writing as 4.32 into 10 to power 6 joules. So remember, again, do not forget to write units in your answer. Okay, moving ahead. Part 2. Part 2, it says, question number 2, part B, it says a wind turbine releases no carbon dioxide in the atmosphere while generating electricity. Compared with coal-fired power station, this is an advantage of using a wind turbine. State one reason why it is important to reduce the amount of carbon dioxide produced. So carbon dioxide causes greenhouse emissions. So reducing carbon dioxide will reduce global warming. So reducing CO2 results in decrease in greenhouse effect, causing reduction in global warming. Okay. Then it says suggest one advantage of using coal-fired power station compared to a wind turbine. So one is the reliability. The wind is not always available. Number 2 is low cost. Coal power plant is low cost. Electricity produced as compared to wind. Wind energy is much cheaper compared to the one that is produced by the wind turbine. So moving ahead, part C, it says a coal-powered power station releases 0.96 kg of carbon dioxide when it generates 1 kilowatt hour of electrical energy. Define 1 kilowatt, define kilowatt hour. So it is the energy generated or consumed by operating a device of 1000 watts for 1 hour. Okay. Then part 2, it says calculate mass of carbon dioxide saved when wind turbine has a power output of 2000 kilowatts and operates for 12 hours. So the kilowatt hours generated kilowatt hours is 20,000. So 2000 kilowatt hour multiplied by 12 hours. This comes out to be 24,000 kilowatt hours. So with 1 kilowatt hour gives 0.96 kilograms of carbon, or sorry, carbon dioxide. Then we have 24,000 kilowatt hours will give 0.96 into 24,000 kg of CO2. So this will be 23040 kilograms. So the mass of carbon dioxide 0040 kg will be there, or just mass of carbon dioxide that is saved because of operating a wind turbine is almost 23,440 kilograms. So moving ahead, part D, it says wind energy is a form of renewable energy. State the name of one other form of renewable energy. Solar energy. Okay, wind energy, solar energy. Other, if you want to add more, tidal energy, geothermal energy. Okay, so any one of them will work. So I will go with the solar energy. Okay, so moving ahead, question number 3, it says the latent heat of, define latent heat of fusion. So this is defined as the amount of heat energy required to change the state of matter at constant temperature. Okay, this is the definition of latent heat of fusion. Then question 3, part B, it says a sample of metal at 100 degrees centigrade is heated steadily until its temperature reaches 400 degrees centigrade. The melting point of the metal is 250 degrees centigrade. Number 1, on figure 3.1, sketch a graph to show the temperature of the metal changes with time. So its initial temperature was 100 degrees centigrade and it is heated till it reaches 400. It was heated steadily. It heated steadily, its temperature reaches uh, the melting point of the metal is 250. So it is heated steadily till it reaches 250 degrees centigrade. Okay. So here is this. Say, for example, this has been done in time t1. Then it stays at this point. Sorry, changes with melting point is this, and it stays there for some time till it gets its latent heat of fusion, and then it again rises from this point till it reaches 400 degrees centigrade. So somewhere here. Okay. This is how it goes. So I call it, let's name it P, A, B. Okay, so this is changes. So the temperature of the metal changes with time, something like this. So this is my T2. This is how my graph would look like. Okay. This point is 250 degrees centigrade. This point is at 400 degrees centigrade. Okay. Let me call this point, say, okay. Just keep it as such. Then part 2, it says a sample with a different material Q has a latent heat of fusion. Then this a sample of a different metal Q has a greater latent heat of fusion than sample P. P and Q are metals with the same melting points, and the sample have same heat capacity. The experiment is repeated with sample Q. The sample is supplied with same amount of energy per, per second as per supplied to the sample P. Explain how the graph of the temperature against time for Q differs from graph in one. So let's draw the graph. So I'm drawing the graph in blue. So the P has, so say for example, this is, let me change the color. So this point, let me call it as P. So this is my sample P. And now I am drawing a Q. So Q, more latent heat of fusion. So Q has more latent heat of fusion. Rest everything is the same. So the graph will be the same till it reaches 250. Now this is the latent heat of fusion region. So latent heat of fusion. Okay, so this is the region. So this will be longer than the previous one. So say somewhere here, and then again with the same slope, you go up till 0.400. So this is again same. So this is for point Q. So the graph of this will look like this. I call it as C. And the time required by this material to be over here is more than the one previous. So explain how the temperature or the graph of the temperature against Q varies. So writing it down, it's a right metal Q takes more times to melt. Metal Q takes more time to melt as its latent heat of fusion is more. The flat region in the graph showing the state change will be longer for metal Q as compared to metal P. Okay, this is how you go with this question. So moving ahead, question number 4, it says two parallel rays of light, one red, one blue, enter a glass prism. Then it says figure 4.1 shows both rays of light before they enter the prism. The blue ray is shown incident on a different side of prism after passing through the prism. Okay. The ray of blue light strikes the left side of the prism at an angle equal to its critical angle, C. Question A, it's part 1. It says on the figure 4.1, mark and label the angle of incidence I of the angle of incidence I and angle of reflection for the blue light as it enters the prism. Okay, so let me label it with the red ink. Angle of incident, angle between the normal and the ray. Angle of reflection, this. So I and R are labeled with red. Then again on part 2, it says continue the path of the blue light after it strikes the left side of the prism. So this is blue light that is going. So remember, we this one statement. So denser to rare medium, rarer medium bends away from normal. Okay, so this is how, or this is what you have to remember. So denser to rarer bends away from the normal. So denser to rarer bending away from the normal. So it would be something like this. Make sure you draw. This is blue light, so let me use the blue ink for this. So denser to rare away from the normal. So this is my normal, this is away from the normal. Okay, so this is blue light shown again. Refractive index of glass for red light is smaller than the refractive index for the blue light. Okay, on figure 4.1, draw the path of red light as it travels in the prism and after it strikes the left side of the prism. So the refractive index is smaller. So this is the red light. I'm now using the red color. So the normal, so both of these normals, remember, would be parallel lines. This one and this one must be parallel. So when you are drawing this, make sure these are parallel. And towards the, so if we are entering from rarer to denser, it bends towards the normal. So it will again towards the normal. So somewhere here, uh, so towards the normal. So, and then now we have a normal here. Again, this normal and this normal are parallel. So another thing we have to remember, red light, since it has a different refractive index, red light diffracts less compared to blue light. Okay, since it has a lesser or smaller refractive index than the blue light, so light refracts less. So if it is moving from the normal, it's moving away, it will move less away from the normal compared to the blue light. So this is your red light. So this is the angle of refraction. This is the angle of incidence here. So these two refraction angles will be different. So red will be going somewhere there, blue will be going somewhere there. So this is how you draw this. Okay, so you have to remember these things. Moving ahead, it says part B, what is meant by the critical angle? So critical angle, it is the smallest angle of incidence for which the light is totally internally reflected. Totally internally reflected. Okay. Then part 2, it says the refractive index of glass for blue light is 1.5. Calculate the critical angle C for blue light in glass. Show your working. So we'll start with Snell's law. Snell's law. Okay. Snell's law states that, say, from a light medium 1, this is your medium 1, this is your medium 2. A light entering from medium 1 will be reflected, and some of the light will be reflected, and the light will be refracted based on, say, this is your medium 1 and this is your medium 2. So refractive index of and sine of angle of 1 will be equal to refractive index sine of angle of medium in 2. So for example, this is N1 is your air and N2 is your glass. So this formula will be A for air, sine of theta in air, then N glass, Ng for glass, sine of theta 2 for glass. Okay. So says refractive index of glass critical angle. So the critical angle is the minimum angle. So let me draw it here so that we'll be able to understand in a much better manner. Say this. Okay. Say the minimum, this is my normal. So minimum angle, so this is here. This is glass. So minimum angle of incidence for which the angle of the light is totally internally reflected, or the angle of refraction is this. Or in other way, if the light is coming from the glass and going into the air, say this is the boundary, this is again glass, this is air, the angle of incidence, this is angle for which the light is totally internally reflected. It is like this as well. It goes this direction as well. Okay, both diagrams are fine. All we need to do is just to make sure that your sine theta and the rest of the angles are adjusted in this manner. So assuming that, we go with the second figure. Okay, since the refractive index of glass is 1.5, calculating. So this is the diagram we go for. Okay, so theta air is equal to 90 degrees. Theta glass is equal to the critical angle, and A is equal to 1, and G is equal to 1.5. Okay, now put in the values. We put in the values, what we will get is 1 sine of angle of C, oh sorry, sine of 90 degrees, and G 1.5 sine of angle of C. Okay, so C becomes sine inverse 1 divided by 1.5. This comes out to be 41.8103 degrees. So the value will be 41.81 degrees. Okay, so this is how you calculate this, and this will be your answer. So moving ahead, question number 5, it says figure 5.1 shows a simple DC motor used in a toy car. Terminal A's and B are connected to battery and the motor rotates. On figure 5.1, add labels inside the boxes, identify the parts for the motor indicated. Okay, so we have to indicate them. So these rings are the split rings or commutators. B, split rings slash commutators. And the A part is actually bush or carbon brush, or you can call it as carbon contacts or the electrical contacts. Then it says state what happens to the rotation of the coil when the number of turns in the coil increase. So the speed of rotation will increase. Speed of rotation will increase. Okay. Then part 2, it says magnetic field between poles of the magnet is reversed. If the magnetic field is reversed, the rotation reverses. Okay, or the direction of rotation is reversed. So moving ahead, part C, it says the power supply to the motor is switched on and off at a steady rate. Figure 5.2 shows how the speed of toy car varies with time as a result of power supply being switched on and off. Okay. Then it says describe the motion of the toy car. So describe the motion of the toy car. That the car basically starts from rest So it starts from rest, speeds up, and reaches a steady state, constant speed. It slows down for some time, but does not reach rest state, and again it speeds up and uh, again speeds up, reaches a steady state, which is equal to its previous state, stays there for some time, and then again starts decreasing. Uh, and this keeps on repeating. Okay. So the car starts from rest, speeds up, and reaches constant speed. It then slows down for some time, but does not reaches also does not reach a steady state, sorry, rest state, and then again speeds up, and reaches earlier achieved constant speed. Okay. This cycle keeps on repeating. Okay, so this is how you're going to write this answer. So then part 2, it says the voltage supplied to the motor is switched on for a longer period of time and off for a longer period of time at a steady rate. Suggest what happens to the motion of the car. Uh, so you can say that the constant speed or the constant speed time of car, speed time of the car increases, or you can call it as because of the more on time. Second part is the car slows down to lower speeds or rest state because of more of time. Okay. If you're going to plot a graph of this, would it will look something like this. So it will start from here, it reaches, then it will decrease something like this. Then it will go up, stays there, it will go down and stays there. So more on time, more off time. Okay. So moving ahead, question number 6, it says a light dependent resistor or LDR is used to sense the amount of light in a room. Figure 6.1 shows the part of circuit used. The LDR is not shown. Okay. Complete this figure 6.1 by drawing the circuit symbol for an LDR between points P and Q. If I have to draw a symbol of an LDR, it looks something like this. Okay, so this is a symbol of LDR. So the symbol of LDR, it would be a light dependent resistor, light ray coming of this, something like this. Okay. Explain how the voltmeter reading changes as the amount of light falling on the LDR increases. So, so more light, less resistance. This is the property of LDR. For example, intensity I naught increases, resistance LDR decreases. So light intensity I naught, if it increases, your resistance will decrease. So let's write it down. So if my resistance will decrease, so then the amount of, so if, for example, if I current is following, if my resistance in the path decreases, my current will increase. So I value will increase. If my I value will increase, the potential dropped, because voltmeter is measuring V equals to I, R. I will increase, the potential drop against, or the voltmeter reading will increase. Okay, so the resistance of LDR decreases. This decreases, causing current in the circuit to increase. This increases the voltage drop across the resistor. Across the resistor, causing voltmeter reading to increase. Okay. So moving ahead, part B, it says figure 6.2 shows a circuit containing three resistors. The current in the 4 ohm resistor is 2.4 amperes. Show that the current in 5 ohm resistor is 1.9 amperes. 1.9 amperes. Okay. So since these two resistances, so resistance goes to 4 ohms and 5 ohms are in parallel. So both resistances are parallel. It means that voltage is same across them. Okay, so both of these resistances, 4 ohms and 5 ohms will have. So I across 4 ohm will be, or the voltage, or similarly, I is equal to V by 5 ohms. So I 5 ohms and I 4 ohms. Both voltages will be the same. So we compare it. So I against 4 ohms multiplied by 4 ohms will be equal to I against 5. I in the 5 ohm resistor multiplied by 5 ohm resistors. And since this both voltage across 4 ohms is equal to voltage across 5 ohms. Okay, both of these voltages will be the same. So if I use this, I is 1.9. Oh, sorry, not 1.9. It is 4 multiplied by 4 ohms multiplied by 2.4 ohms is equal to I into 5 ohm resistor multiplied by 5 ohms. So I in 5 ohm resistor is equal to 4 multiplied by 2.4 divided by 5, and this comes out to be 1.9 amperes, hence shown. Okay, then it says calculate potential differences between point X and point Y. So the potential difference V between X, Y is equal to potential difference across 4 ohm resistance is equal to potential difference across 5 ohm resistance. So if you know the value of current, just multiply it with the value. Oh, sorry, no. It's my bad. So potential XY is potential difference that is dropped across the 4 ohm resistance or 5 ohm resistance plus potential across the 6 ohm resistance. So any of these potentials, so V 4 ohm is equal to V 5 ohm is equal to 4 multiplied by 2.4 volts. This is the potential difference. Or if I multiply 4 multiplied by 2.4, it comes out to be 9.6 volts. This one plus the current I that is flowing across this. So first of all, I have to calculate the current I. The current I will be equal to I 4 ohms plus I in the 5 ohm. I in the 5 ohm resistance. 4 ohm resistance is 2.4 plus I in the 5 ohm resistance is 1.9. So 1.9 and 4.2 is 1.9 plus 2.4 is 4.3 amperes. So 4.3 amperes current is flowing, and this I is equal to 4.3. This is 1.9. This current is flowing. This divides into 2. So the backward, if you calculate backward, this is 4.3. The voltage across 4 is 9.6 volts plus voltage across. So V across 6 ohms, we can be calculated as I cross 6 ohm multiplied by R. So I cross 6 point is 4.3 multiplied by 6. This is 4.3 multiplied by 6 comes out to be 25.8 volts. Okay. And then Vxy will be equal to 35.52 volts. So my answer will be 35.52 volts. Okay. So moving ahead, so this is how we solve this question. So now our section A is done. Now we move to section B. In section B, we have to answer 2 of these questions, but we'll be solving all the questions which are available to us in this. So question 7, it says 7.1 shows a toy helicopter. It can hover and travel through the air. A student flies the toy helicopter on a journey from A to B to C to D at a constant height. Okay, so this is from A, we can see that A to B to C to D. Determine the total distance traveled by the helicopter. So total distance traveled will be 10 meters. So 10 meters plus 35 meters plus 40 meters. So total distance will be 85 meters. Okay. The toy helicopter makes a journey in 40 seconds. The average speed equals to distance over time. So this is 85 meters divided by time is 40 seconds. This comes out to be 2.125 meters per second. So 2.125 meters per second. Then moving ahead, it says state the difference between distance and displacement. So displacement is a vector quantity, whereas distance is a scalar quantity. This is the difference between a distance and a displacement. It says determine the scale used in figure 7.2 and complete the sentence. 1 centimeter on the diagram represents. So what you will be doing? 1 centimeter on the diagram represent dash on the uh, part. So you can use uh, a ruler and measure. Say for example, this is this whole length. Measure length AB. We are going to measure length AB. That comes out to be say X centimeter with the help of your ruler, and the actual AB is equal 10 centimeters. So using it, say from uh, so from ruler, so from ruler, if you say measure AB, it comes out to be X centimeter. So divided by, so, and actual AB is 10 meters. So X centimeter is say 10 meters. So 1 centimeter will be 10 divided by X meters. So just simply 10 divided by X, whatever you will be measuring on your answer sheet, put the value over here, that is centimeter, and then divided by this would be, answer will be 1 centimeter will be equal to dash number of meters. Okay. Then figure 7.2, measure the displacement of point D from A, show your working. So measure the displacement. So you can always use a ruler and measure this value. Okay, so measure with the help of ruler, you can measure this value. Another way is to this is 35. This is 30. This is 35. You can always use so AD, show your working. So it will be 30 square plus 35 square whole under root. This comes out to be 46.1 meters. The size of displacement. The size of displacement. Again, this you have to, the size of displacement from A to B. So if you are going to use, so this will be 46.1 meters. Or you can use a ruler to measure it measure with ruler. Say it comes out to be Y centimeter distance AD, then Y. So this size of displacement will be Y multiplied by 10 divided by X. So whatever your measurements X and Y, just use them and find out this value. This value must be comparable to this value. Okay. So this is how you will be able to calculate it. Then it says determine the angle between north and the direction of displacement D from the point A. So on this figure, draw a straight line. This is, and measure this angle. Okay. So it says okay. So say determine angle between north and the direction of displacement from point D to A. Okay. So from point D to A, if we go back, so from point D to A, so displacement is in this direction. This is my north direction. This is the angle. So I have to calculate this angle. So we have a triangle like this. So we have a triangle like this. So this is 35, this is 30, and this is the angle, and this is our north. Okay. So we have to calculate this angle. So this angle or is theta. So this theta is actually tangent of theta 30 divided by 35, tangent inverse of 30 by 35. This comes out to be approximately 40.6 degrees. Okay. Then part 5, it says what is what is meant by velocity? It is the rate of rate of change of displacement with time. Okay. Then it says another toy helicopter flies directly from A to D in 40 seconds. Explain why the magnitude of velocity of this helicopter is smaller than the answer in part 2. So the helicopter follows the shortest distance between A and D. The distance is smaller is smaller compared to the distance in result of A2. Thus, lesser magnitude of velocity. Okay. Or if you have to calculate the magnitude of velocity, it will be 46.1 divided by 40, approximately equal to 1.15 meters per second. Okay. So then part 2, it says when the toy helicopter hovers at D, its motor fails and it falls. It reaches terminal velocity. As it falls, explain the terms and the forces of acceleration that happens. Forces of acceleration, what happens as the helicopter falls and reaches terminal velocity. So the helicopter falls and accelerates under the gravity. So accelerates due to the gravity or under the gravity. The air friction force increases as it falls at an instant. The force of uh, air resistance becomes equal to the force of falling. So following the net force acting on the helicopter becomes 0. The helicopter then falls under constant velocity that is called terminal velocity. Okay, so for example, this is your helicopter. It is falling. This is falling under the gravity, because of, no, I'll not call it D. It's falling because of its weight. And then there is air resistance that is acting on it. So at a point when comes that when force becomes equal, force of resistance because of air becomes equal, at that time it falls with the velocity v terminal. Okay, this is how it will happen. So the helicopter falls and accelerates under the gravity. Number one, the force of friction starts to increase as it falls. Number two, the instant at which the air resistance become equal to the force of following. Number three, uh, the net force acting on the helicopter becomes zero. Number four, and at that point, the velocity of the helicopter is the terminal velocity. That is the fifth point. So these are the 5 points you need to mention to complete, to secure complete credit for this course or for this question. So moving ahead, question number 8. It says the figure 8.1 shows a water manometer. When the water manometer is connected to a sealed container and the tap is opened, the water level changes as shown. Okay. So initially this is the initial case, and then shows when the tap is open. So then first part, it says define pressure. The pressure is the force acting per unit area. Force acting per unit area. Okay. Then part B, it says explain why the water levels are the same on sides of the manometer in figure 4.1. So the pressure in 8.1 is same on the both sides, air over here and air over here. Okay. Okay, so both sides the same atmospheric pressure. The pressure on both sides open ends is the same, i.e. atmospheric pressure. Okay. Then it says, explain why water level changes when gas tap is opened with manometer connected in figure 8.2. So the gas exerts pressure on one side, which is greater than the atmospheric pressure on the open end. Then in part C, it says explain why water levels stop changing at the level shown. So the pressure, the force exerted by the gas, or the pressure exerted, force exerted by the pressure on the gas, it becomes equal to the atmospheric pressure exerted by the column of the water. So the pressure exerted by the gas on water becomes equal to the atmospheric pressure exerted by the column of water. Okay. So moving ahead, part C, it says the water in the manometer has a density of 1000 kilogram per meter cube. Atmospheric pressure is 1 into 10 to the power 5 pascals, and the gravitational field strength is 10 to the power 10 meters per second. Calculate the pressure inside of the gas inside the sealed container. Give you answer to 3 decimal places. The pressure of gas is equal to pressure atmospheric plus pressure of the water column. So atmospheric pressure 1 into 10 to the power 5 pascals, water pressure plus rho GH. So rho GH, if we are going to see, it will be 1000 plus 10 multiplied by 10 into height was 40 divided by, 40 divided by 100. So if we are going to see, this length is, this is 30 here, this is 70 here. So this comes out to be 70 minus 30, 40 centimeters. So, and we have to measure or use the units in meters. So that is why we have changed it. So it comes out to be 4,000 pascals, 10 to the power 5. So it would be 4,000 pascals. So three significant figures, 104 pascals. Okay, pressure is this. Or other ways to write 1.04 into 10 to the power 5 pascals. Both our answers are correct. So moving ahead, part D, it says the temperature of gas inside the sealed container increases. Use ideas about molecules to explain why the water levels change. So as the temperature increases, these causes the molecules of gas to certain temperature increase causes increase in average kinetic energy of the gas molecules. This causes them to vibrate more frequently, resulting in more collisions per unit area, thereby increasing pressure. The increase in pressure changes the length of the water column. Okay, so this is how you write this answer. So moving ahead, part E says the manometer is not suitable for measuring gas pressure of 2.5 into 10 to the power 5 pascals. Okay, explain why. So the maximum pressure of, so if we remember, so the pressure with the formula we used, the pressure of gas, ATM, and atmospheric column. So pressure of gas it can measure, it was atmospheric pressure plus rho G and H. So the maximum H it can measure is somewhat up to 100. Say in ideal case, it can measure something from this level onwards. So up to 100 centimeters of maximum H max it can measure is 100. Okay. So the max of centimeters. So this will be 10 to power 5 plus 1000 multiplied by 10 into 1. So 2 into 10 to power 5 is the maximum Pascal it can measure. So the maximum it can measure is up to 2 into 10 power 5. So if the pressure is more than this, the gas is unable to measure it. So again, let's write it here. So pressure of gas it can measure is pressure, atmospheric pressure plus rho gh. And rho gh is defined or limited by H max. H max is 100 centimeter is equal to 1 meter. So the pressure of gas max it can measure is with this column of length is 2 into 10 to power 5 pascals. And out of that, there is no long. So no more length of water that can be available to us. So explain why the max pressure of gas, the manometer can measure is 2 into 10 to power 5 pascals. The manometer not have the physical length of water to sustain the extra pressure and give accurate reading. Okay. Then part 2, it says states one change in manometer that allows it to measure pressure of gas 2.5, 10.5 in a normal school lab. So instead of water, use higher density material, say mercury, or change the length of column to more than. So use a high density fluid instead of water, or number 2, use higher column uh, of length greater than 150 centimeters. Okay. So moving, so this is how we address the question. So last question for this exam, question number 9. It says table 9.1 shows details of 7 nuclides. So hydrogen 2, 3, francium 223, iridium 192, phosphorus 32, radon 222, and technetium 99. Emitted radiations again, none, beta, beta, gamma, beta, alpha, gamma, and the half-lives are given. Okay. Hydrogen 2 and hydrogen 3 are isotopes of the element of hydrogen. Define the term isotopes. Isotopes, same number of protons, different number of neutrons. So same. So two or more elements. Two or more elements with same number of protons, but different number of neutrons, okay, are called isotopes. Then part 2, it says the equation of decay of phosphorus 32 as it emits beta particle is given. Explain whether the equation shows that Q is an isotope of phosphorus. Q is not a chemical symbol for an atom. Okay, so Q is an isotope or not? So if we see P, the atomic number, and mass. Atomic number is this, mass number is this. So number of protons is equal to mass number of neutrons is 32 minus 15, equal to 17. Okay, so this is the number of neutrons and number of protons, that is T we have. So same number of neutrons but different number of protons. It do not have same number of neutrons, so it means same number of protons but different number of neutrons. So do not have the same number of protons. So the element Q does not have same number of protons and have same number of protons as of element E. Yeah, protons, it is not an isotope of P. Okay, then part B says one of the sources in table 9.1 is used in medical procedure to detect unusual bone structures. It is injected into the patient and radiation emitted is detected outside the body. State which source in table 9.1 is more suitable for this type of medical use. Such medical use, number one thing we need is a very it's a half-life that is not very small, but not goes into days or years. So 6 hours is a good one, 22 minutes is also a relatively good one. Then 12 years not, 74 day not recommended, 4 day, this is also not recommended. So these two can be our choices, but if we have to measure bone fragmentation or the bone structures, betas cannot penetrate them, only gamma rays can penetrate them. So the gamma one would be the ones we choose. So technetium 99 would be the best choice. 99 is the one we'll be using. Explain 2 reasons for your choice. So gamma rays can only penetrate through human body and can be detected. The half-life is good for measurement without good for measurement and decays readily without damaging the human body. Okay, so these are the two reasons why this is the best choice we have. Then it says part C, radon is one natural source of background radiation, some causes background radiations are man-made, for example, X-rays. State one other natural source of background radiation is a cosmic rays. Cosmic rays is a natural source of radiation. State one man-made source of background radiation. Nuclear weapons are one. Nuclear weapons are one cause of background. One harmful effect of background radiation. Mutation. Mutation of cells, cancer, uh, other cellular damage, cell also called genes, etc. Things like this. Moving ahead, part D says one fusion reaction that occurs 2,1H plus 3,1H gives 4,2He plus dash dash X. So hydrogen atom, another hydrogen atom. So basically two isotopes of hydrogen adds together to form helium, and then there is another. Complete the equation. So we have to basically complete this equation. So 2 plus 3, 5. We are getting 4 here, so 1 will come here. 1 plus 1 is 2, so this one will be 0. Okay, just simple maths, nothing else. Reduce the name of the particle X. So if particle has there's no protons, but has some mass, so it's a neutron. It's a neutron. Suggest where this fusion reaction takes place. So it's a reaction sun. It takes place in stars or in hydrogen bombs, unfortunately. So moving ahead, part E, it says compare the properties of alpha particles and beta particles in terms of their ability to penetrate through materials, ionization effect, and deflection in the magnetic field. So alpha particles are blocked by thin sheet paper, whereas beta particles can pass through these and can be blocked by sheet of aluminum. Okay. Number 2, ionization effect. Alpha particles are more ionizing than beta particles. Part C, deflection in magnetic field. So beta particles can be deflected more in magnetic field than alpha particles. Beta particles can even be deflected back, whereas the alpha particles have much less deflection. Okay, so this is how you answer this question. So here is the end of this exam. I hope you have understood something with this effort, and I wish you best of luck for your exam and your preparations. See you in the next video. Thank you very much.